All right. So first of all, make note, our next exam is next week. It's going to be on Wednesday and Thursday of next week. So please make a plan as to when you're going to go about taking that exam. We will be all finished up with this new material that by the end of this week. We'll finish up our electrochemistry lecture today. The last chapter that we're going to cover, nuclear chemistry, we're just going to have one lecture on, all right? So we'll be able to button that all up on Friday, okay? So that means next week on Monday and Wednesday, we'll do a little bit of review, all right? And then you'll be prepared for your exam on Wednesday and Thursday. All right, so let's finish talking about batteries by looking at a battery here, a double, triple, whatever battery here, all right? And let's see if we can pick apart these components here. So first of all, does anybody remember looking at a battery, right? You got that plus minus sign. That's how you got to put it into your calculator or remote controller, wherever it may be correctly. Which end's which? Does anybody remember? The little bump is on which end? The positive end. All right. So now we got some fancy terminology we can apply here, right? So this is our positive end. This is our negative end. Okay? Remember, we're supposed to have that one phrase in mind, from blank to blank. What do we remember? From what to what? From anode to cathode. Okay? And so if electrons are negatively charged, right, they want to go to the positive end of our battery. So which one of these is our anode and which one's our cathode? The positive terminal is going to be the cathode, where the electrons go to, right? And so then they originate at the anode. So here's our cathode of our battery. Here is our anode of our battery. Okay, and so batteries are made of zinc and manganese oxide. All right, and let's try to figure out which reaction is occurring at which terminal here. For that, we need to go to our handy-dandy constants page. Not that. This thing here. All right, so take a second and see if you can identify which reaction would occur at which terminal here. So I got my manganese 4 oxide up here, and my zinc is all the way down at the bottom here. At the top of the list is what? The reduction or the oxidation reaction? Reduction's at the top. So my oxidation reaction, I got to flip it, but those are going to be the ones at the bottom. Okay? So the reaction that's taking place, whoops. Nope. At my cathode is going to be my my reduction reaction. All right, so that will be the manganese 4 oxide. And at my anode is the oxidation reaction. So that would be my reaction of zinc. Okay, so these are these reactions that are powering batteries. This is Truthfully, this is sort of an old school battery here. New battery technology is getting better and better, and they're getting fancier and fancier. This is kind of a simplistic view here. But absolutely, especially early on, this is exactly how a battery was made here. The manganese oxide is actually like this paste that sits in the middle here and reacts with your zinc at your anode. All right, but we get this transfer of electrons from our anode to our cathode. And really, we connect it, and there's this wire, right? So really, we're sending the electrons through this wire, and that's what's powering our remote control or whatever it may be. All right, so let's take a look at these formulas real quick, because we talked about oxidation and reduction half reactions. Now we need to figure out which element is being oxidized and which element is being reduced in a particular reaction. And for that, we need to learn how to do oxidation numbers. All right, so I'm going to put down a few compounds. We'll look at an actual reaction here in a second, but let's look at just some compounds all by themselves. All right, and so our goal is to calculate oxidation numbers for these compounds. All right, and we got some rules here that we got to know. So first of all, oxidation number is a lot like charge, this concept of charge, right? If you know the charge on an ion, it tells you how many electrons are sitting on that particular element, right? A charge of -2 means there's 2 extra electrons. A charge of +2 means that it's missing 2 electrons, right? So this concept of charge really only applies to ionic compounds, okay? But of course, when we have covalent compounds, these covalent bonds are also made up of electrons. So oxidation numbers is kind of like this extension of this concept of charge that also applies to covalent compounds. And it tells you where the electrons are distributed within that covalent compound. Which element is holding more electrons, which elements are holding fewer electrons. Okay, so very similar to charge, but something that we're going to be able to extend to covalent compounds as well. All right, so first things first, our first rule. Oxidation number of atoms in their elemental form. So what the heck do I mean by that? Meaning all by itself, not in a compound with any other element. Is always 0. All right, so I lied. I'm going to make this example a little harder. We're going to make it the zinc chloride here, ZnCl2. All right, so out of all of our examples here, do I have anything in its elemental form? The zinc, right? The solid zinc, that's zinc's elemental form. It's not in a compound with anything else. So its oxidation number is just 0. Right? Rule 1 does not apply to these other 2 examples, okay, because these are both compounds. So then we got to move on to rule 2. Oxidation number of monatomic ions is the same as their charge. All right, so what the heck do I mean by a monatomic ion? Let's pick that word apart. What do we think the mon means? Mono, right? Mono meaning one, right? Monatomic ion is then a single atom ion, right? So monatomic means single atom ion, i.e. not a polyatomic ion. So if we have an ionic compound that consists of monatomic ions, we can figure out the oxidation number just by looking at the charge of those ions. All right, so here we have these two ionic compounds here. All right, so let's review something that hopefully we all know from first semester, but just in case, and that's how to figure out the charge of these ions here. All right, so based on where these live on the periodic table, I can figure out the charge on these ions. Well, for some of them. So we got to bust out a periodic table. I have 1,000 of somewhere. All right. Don't worry about all this. Diatomics, great. Okay. So everything that lives in this first column here likes to form ions with what charge? +1. What about the next column over? +2. All right. We got to skip these transition metals because these are elements that you don't know the charge just by looking at the periodic table. We're going to have to work backwards from these ones. All right, but we can jump to the other side. Our noble gases, what type of ions do they like to form? Yeah, trick question. They don't form ions, right? They're perfectly happy the way that they are. They don't want to give up electrons. They don't want to accept electrons. So 0. What about our halogens? -1. The next column over, the chalcogens or something like that. -2, -3. Okay, so based on where an element lives on the periodic table, we can figure out what its charge is. All right, so let's just take that first example. Zinc chloride. All right, one of these elements, right off the bat, I can tell you what its oxidation number is based on where it lives on the periodic table. What is that? Which element? The chloride, right? So I know my chloride is -1. Okay? My zinc is a transition metal. I can't tell just based on where it lives on the periodic table. So I'm going to have to work backwards from the formula here. What I know is that I have these 2 chloride ions. And I know that each one has a charge of -1. So in terms of the total amount of negative charge in this molecule, what is that going to sum up to? -2. And that has to be counterbalanced by what charge? +2. So my zinc ion here has a +2 charge. Okay. All right. So now let's do the other one. I want you to tell me, everybody's going to take a second and tell me the oxidation number of oxygen and manganese in this compound here. All right, which one's the easy one? Oxygen. And how can I tell what oxygen's oxidation number is? Because it lives right here on the periodic table. All right, so that's going to be -2. Now we got to use this formula to work backwards and figure out what our manganese ion's charge is. If I got 2 oxygens, each of them have a charge of -2, what's that going to sum up to? -2 plus -2 is -4. And that's got to be counterbalanced by a charge of +4. So this is the manganese 4 ion. All right. All right, so that's all well and good. Now let's do another example. We're going to put 2 more down. So this gets us through sort of simple ionic compounds, but again, the whole concept of oxidation numbers is that it extends to covalent compounds as well. So how do we deal with covalent compounds? The oxidation number of the most electronegative element in a covalent compound. Whoa. Is the same as its ion's charge. All right, so for these 2 examples here, how are we going to get these? We're going to build these little Lego people at the bottom here. And we're going to have 1 for each element. All right, and in that top circle, we're going to do the oxidation number of that element. All right, and then in the bottom box, what we're going to keep track of is the sum of the oxidation numbers. All right, and I'll show you why, and we'll see why this is important here in a second. So for these 2 compounds here, we can't get both of these elements yet. We haven't done all of our rules yet. But we can get the oxidation number of the most electronegative element in each of these compounds. All right, so maybe we should review electronegativity real quick. This would be one of these periodic trends that you would have learned about in the first semester. All right, and of course, and it pertains very much so to these oxidation numbers. Okay. Electronegativity is an element's ability to pull electron density in a covalent bond. So what the heck does that mean? Okay. Covalent bonds. 2 elements are sharing these electrons. All right? But they are always in this tug of war over those electrons. Both elements want to pull that electron density onto themselves. All right? Turns out that some elements are better at tug of war than others. Some elements are better at pulling electron density onto themselves. So when they're in a covalent bond, they're actually hoarding a bunch of that electron density on themselves, leaving the other element relatively electron deficient. So that's this concept of electronegativity. Which element is the best at tug of war? All right, that's the one that's going to hoard electron density within that covalent bond. And which element on our periodic table is our most electronegative, is the best at tug of war? Fluorine. All right, everything points towards fluorine. Fluorine is the most electronegative element. And you can tell how electronegative all the other elements are based on their proximity to fluorine. All right, the closer you are to fluorine, the more electronegative you are. All right, so our trends are this direction and this direction. Everything points towards fluorine here. Okay, more electronegative means closer to fluorine. All right, so we had this compound, CF4. If that's a covalent compound, right? Two nonmetals. But I can tell my oxidation number of the most electronegative element in that compound because it's going to be the same as its charge if it was an ion. So between a compound with carbon and fluorine, what's the most electronegative element? Fluorine. It's always fluorine, all right? So then what's the oxidation number of the fluorine? It would be the same as the charge, right? And so given where fluorine lives on the periodic table, that's -1. All right, so I can tell the oxidation number of fluorine, I'll just use a different color, is -1. All right, the other box we're going to be able to fill in here is we're going to sum up the oxidation number of all 4 of those fluorines. So what am I going to put in my square? -4. All right, and we'll see why this is important here in a second. Notice that at this point, I still can't do my carbon yet. We need one more rule. So our last rule here, oh no, I lied. Let's just jump over here. All right, everybody take a second, copy down this formula. We're going to go back to our periodic table, and you're going to tell me which element you can assign an oxidation number to in this compound. All right, oxygen is right next door to fluorine. So oxygen is the most electronegative. Oxygen is actually the second most electronegative out of all of our elements here. Okay, so it's a good one to keep in mind as just also being very electronegative. But yes, in our sulfate ion, I can do my oxidation number of oxygen. It's going to be the same as the charge on an oxide ion, which is -2. So then if I sum it all up for all 4 oxygens, what am I going to put in my square? -8. All right, so I still haven't been able to do my other element yet. So how are we going to do that one? The sum of all oxidation numbers is equal to the net charge on that molecule. All right. Oh, well, whatever. So in order to figure out my carbon, I have to work backwards. All right. I don't know what the oxidation number of carbon is, but I do know what it is on my fluorine. And I know that the sum of all of these together has to equal the net charge on this molecule, which is 0, right? There's nothing written there. So my net charge is 0. So this is what allows me to work backwards and figure out what my oxidation number on carbon should be here. Right? What plus 4 is going to give me 0? Oh, I'm sorry. What minus 4 is going to give me 0? Plus 4. And there's only one carbon in this formula, so the oxidation number on that carbon must be plus 4. All right, so given what we just discussed, given that example, see if you can't figure out what it is in sulfur for my sulfate ion here. What up? It's not the same as an ion, but it does tell you that the carbon has way less electron density than the fluorines do. So it's analogous to charge, but it doesn't necessarily mean that it's going to fall apart like ions do. It just tells you that in that molecule, each fluorine has a lot of charge density, and the carbon in the middle has very little electron density. All right, so I don't know what my sulfur is, but I know that everything has to sum up to what? -2, the net charge on that polyatomic ion. So then I just got to ask myself, what -8 is going to leave me with -2? Plus 6. And there's only one sulfur in this compound here. So its oxidation number must be plus 6. All right. All right, so then you're going to do one from scratch for me. Wait, I lied. I'm going to change it. It's BrO3 minus 2. More interesting. All right, so we're going to do our Lego people. We're going to look on our periodic table. Which element is the most electronegative out of these two, bromine or oxygen? Oxygen. So we know its oxidation number must be -2. So sum it all up, that's -6. All right, and the net sum of all my oxidation numbers have to equal that charge of -2. So then what's the oxidation number on the bromine? +4. All right, so what is this going to help us do? Again, it's going to help us determine which element is being oxidized and which element is being reduced in an oxidation-reduction reaction. So let's take a look at a reaction here. Not just a single compound formula, but an actual reaction. All right, and what we're going to do is we're going to build this table where we have each element, sodium, sulfur, and oxygen. And we figure out its oxidation number first on the reactant side, and then on the product side. All right, I gave you this balanced chemical equation here because it was going to drive me nuts if it wasn't balanced. All right, but let me just say the coefficients do not factor into how you determine oxidation numbers. You just look at the formulas of those compounds. All right, so take a second and see if you can't fill in this table here, and then we'll go do it together. All right, so let's do it. So first of all, if I look at my rules, rule 1, the oxidation number of atoms in their elemental form is 0. Do I have any atoms in their elemental form here? Yes. Where do I have an atom in its elemental form? The oxygen on which side? The product side, right? Oxygen is all by itself. Yes, it's a diatomic. Oxygen is a diatomic element, but that is oxygen's elemental form, O2, right? It's not in a compound with any other element. So my oxidation number for oxygen on my product side would be 0. Do I have anything else in its elemental form? No. All right, so now I'm going to move on to Rule 2. Rule 2 says that if I have any monatomic ions, their oxidation number is going to be the same as their charge. All right, so let's take these two last compounds individually. Sodium sulfide. Is this an ionic compound? Yeah, maybe we should just review. How do we tell if it's an ionic compound? Metal and nonmetal, right? If one thing lives on one side of the periodic table, the other thing lives on the other side of the periodic table, that's an ionic compound. All right? So this is an ionic compound. So if I know the charges on these two monatomic ions, then I know what their oxidation number is. And where do we get charges? Again, by looking at where they live on the periodic table. Okay, so again, we can get our periodic table, put in +1, +2, jump to the other side, -1, -2, -3. I have sodium and sulfide. All right, so my sodium ion has a charge of +1. My sulfide ion has a charge of -2. These are just monatomic ions, so their oxidation number is going to be the same as their charge. So sodium sulfide, this was on my product side, so sodium is +1. Sulfide is -2. All right, and notice that my Lego rule still applies, right? If I wanted to say, okay, +1, sum that all up, that's +2. This one's -2. There's only one of them, so those sum up to 0. That checks out. All right, but we didn't have to make it that complicated, right? We could just look up what the charges of these ions were based on where they live on the periodic table. All right, so now let's take our other compound, the sodium sulfite. Is this an ionic compound or a covalent compound? So this is also an ionic compound. Do I have any monatomic ions? I got one, right? My sodium is a monatomic ion, so if I know its charge, I know its oxidation number. Okay? What's the charge on a sodium ion? Didn't change from when we figured it out when we looked it up before, right? But my sulfite ion is not a monatomic ion. It's a polyatomic ion. So that sulfur and that oxygen are covalently bound together. So now I got to do my Lego people to figure out what the oxidation numbers are here. All right? So, and actually, you can convince yourself of this on your own. If you did it with this compound as a whole or just the sulfite ion, you would get the same answer. I'll do both of them just to be good. All right, let me get my Lego people here. All right, and in order to do this, we got to first fill in what we know. All right, so again, we knew that our sodium was +1. Jeez Louise, come on. There we go. Whoops. I have 2 of them in my compound, so if I sum everything up, that's +2. Okay? But for my polyatomic ion, now I got to go to my next rule here. The oxidation number of the most electronegative in a covalent compound is going to be the same as the charge of the ion, of that element when it's an ion. So, we kind of already did this one. That was my bad. Anyways, what's going to be the more electronegative element, oxygen or sulfur? Oxygen. Look, unless oxygen's with fluorine, it's always going to be oxygen, right? And that is a very helpful rule to remember because so many of our polyatomic ions have oxygen in it, right? Think of all those balancings that we did at the first time. We added water to balance oxygens. Oxygens are all over the place, all right? So just a good rule to keep in mind that my oxidation state of my oxygen is going to be -2 when it's in a covalent compound. Okay, so take a second and finish this up. You could do either one of these and you would arrive at the same answer. Okay, but see if you can't figure this out. Finish off our table here. All right, so if I'm going to do my compound as a whole, everything would sum up to 0. So 2 plus -6 gives me -4. What -4 gives me 0? +4. All right, and notice that I'd arrive at the same answer if I did it looking at just the ion. What -6 leaves me with -2? Also +4. All right, so this table here, when we fill it out for our products and our reactants, we can see which elements are being oxidized and which elements are being reduced. Okay. Remember, losing electrons is oxidation. All right, but it's kind of a weird way of thinking about it because electrons are negative charged. What I think is the easiest to do is look at this table here and see which oxidation number is going down, because oxidation number decreasing means that that element is being reduced. And I don't know, for me that's easier to remember. Going down means reduced. Great. Okay, so which element is being reduced in this particular reaction? The sulfur, right? It's going from +4 to -2, so it's going down. All right, so then the one that's going up is the one that's being oxidized. Okay, so what does this help us do? It helps us identify which element is actually being oxidized, which element is actually being reduced. What's the sodium doing? Yeah, just chilling. Jack crap, right? Not doing anything in this reaction. It's just serving as a counter ion in this particular reaction. What's actually sort of the meat of the reaction here is your oxygen losing electrons and your sulfur gaining those electrons, right? So that's what our oxidation reduction table helps us do. What's up?
Why is it that the oxygen the oxygen gains 2, but the sulfur loses 6?
So now all of a sudden you'd have to consider your balancing in your chemical equation if you're talking about number of electrons being exchanged. But if we just look at oxidation numbers, we can figure out which element is losing and which element is gaining. All right, that's all I got for today. All right, so we'll pick up next time, and next chapter we'll do our one lecture on nuclear chemistry, and then you are done with all new information for Chem 1B for this semester. So, nice job.